from MIT, where he won the award for Best Doctoral Dissertation in Theoretical Computer Science. He then spent some time in Princeton, and he has recently joined Harvard. He's done some really lovely work on a variety of problems, kind of sparse Johnson-Lindenstrauss, kind of streaming algorithms, linear algebraic problems via sketches. So thanks very much. Oh, and so I forgot to mention about Sedipto. So Sedipto drinks more coffee than anyone else I know. Jelani types faster than anyone else I know. Okay, over to Jelani.
So what I'll talk about is based on a few different joint works with Daniel Kane and also with Hui Nguyen. And I'm going to focus first in the talk on dimensionality reduction for some generic problems in high-dimensional computational geometry. And then toward the second half of the talk, I'll focus in on numerical linear algebra. Okay, so the first part of the talk, we're going to talk about the Johnson-Lindenstrauss lemma, which says that if you have capital N vectors and you want to preserve all the pairwise distances up to 1 plus epsilon, you can map those vectors down to 1 over epsilon squared log n dimensions, independent of the original dimensions of the vectors. And it's been used to speed up some geometric algorithms. So, first you reduce the dimension down, and then you run whatever algorithm you had before. It also has showed up. There are many, actually, bullets for the second one we're going to see later. But using it in, say, a black box way in numerical linear algebra, and it's also basically equivalent to a kind of matrix needed for compressed sensing. Okay, the kind of matrices that you get out of this. How do you prove the Johnson-Lindenstrauss lemma? So one way is you prove some kind of probabilistic lemma, such as this one first, which says that if you have any vector u, then if you pick a random matrix from a certain distribution, it'll preserve the norm of u with high probability. And the number of rows you need in the matrix depends on the distortion parameter epsilon as well as the success probability delta, 1 minus delta. And how do you prove the metric JL based on this distributional JL? Well, you set delta to be 1 over the number of points squared, and you union bound over all the difference vectors. Okay? So that gets you the bounds that I said on the last slide. And in fact, these bounds are near tight in metric JL and tied up to a constant factor for distributional JL. Okay? Okay. So what do we do with metric JL? So how do the proofs before work to come up with such a distribution? Basically, all these proofs before took a random matrix, a random dense matrix, like IID sign entries or IID Gaussians, and showed that that gave the distributional JL that I talked about on the last slide. The downside is that if you use these dense matrices, then doing the embedding is dense matrix vector multiplication, and it takes you the following amount of time. I'm using the 0 subscript to denote the support size of the vector, right? So m times the support size of the vector. Okay. And there has been work about speeding that up. Okay. So the first work that looked at speeding that up, asymptotically, was by Ilon and Chazelle, using what they call the fast Johnson-Lindenstrauss transform. And I'm not going to get into the details of how it worked, but the bottom line is you can embed a vector in n log n time, okay, close to n log n. And there have been subsequent works about getting that m cubed out of the picture, maybe at the expense of slightly increasing the target dimension. But the downside of these works is that it's slow to embed sparse vectors. Kind of if you look at the proof of why these constructions even work in the first place, they sort of say, after I apply h and d to my vector, it'll be well spread with high probability so that the P matrix works. And basically what that means is you destroy sparsity to get the correctness of your algorithm. So they're not fast for sparse vectors. Okay. And I claim that we often do care about sparse vectors. We care about embedding sparse vectors because in a lot of applications, say especially in machine learning, the vectors that you want to embed are sparse. So treating documents as a bag of words where the dimension is the lexicon size and the ith entry is, say, some weighted count of the number of occurrences of word I. Or look at a matrix where, the ijth entry, say in the Netflix matrix, you have users and you have movies and then you have ratings. Most users don't rate every movie in your database. So you expect sparse vectors all over the place. So we want embeddings that work well for sparse vectors. Okay. So one way to embed sparse vectors faster is to use sparse matrices. So I said in the distributional JL lemma, you pick a random matrix from some distribution and show it works. So pick a distribution that's supported on sparse vectors, on sparse matrices. And what do we show in the work with Daniel Kane? So let S be the number of non-zero entries in the embedding matrix that you get out of the distributional JL lemma. The original works of Johnson-Lindenstrauss and those other contemporaries is that you get S to basically be M. Okay. Akliopta showed that you can maintain the same exact M, even the constant factor, and get S to be smaller by a factor of 3. So he saves a factor of 3 in his embedding time. And kind of what we show down at the bottom is that you can maintain the same M up to a constant factor. We don't get the same sharp constant that previous work got. But S is actually better asymptotically. It's better by a factor of epsilon. So it's always better than using the previous matrices. And we also showed in work with Wynne that for any M which is less than poly 1 over epsilon times log of the number of points, you basically need an S that's very close to that, up to this log 1 over epsilon factor. So this bound is almost optimal. Not just the analysis of our construction, but any map, any linear map that provides an embedding must have large sparsity. Okay. And I should also mention that if distributional JL, the dependence on delta should be log of 1 over delta. But if you're willing to blow that up to 1 over delta, you can even get sparsity 1. And that's from work by Thorpe and Zhang. So, what is our mapping? So there was previous work by Dasgupta, Kumar, and Sarlosh on getting sparse JL. And basically, what does their mapping look like, their dimensionality reducing map? So at the top here, I have the vector u, which I'm trying to embed. And I'm trying to embed it into m dimensions. So here there are n buckets, n is the original dimension, and here there are m buckets, the target dimension. And what their mapping looks like is for each coordinate, you just randomly hash it to s places, where s is the sparsity, okay, with replacement. And when you add it to a bucket, you first pre-multiply by a random sign before you add it. Okay? That's their mapping. And what do we give in our work? Well, first we just show that if you just hash without replacement, instead of log squared 1 over delta, you get log 1 over delta. And in fact, that's not an artifact of the analysis. You can show that if you hash with replacement, you really do need log squared. And we also give a different construction, which is basically, if you draw it the right way, the count sketch from the streaming literature, which says that in the target space, you're going to break up your m blocks into m coordinates into s blocks, each of equal size m over s. And then you're going to hash each coordinate to one location in each block and add it with a random sign pre-multiplied. And we show that that gives the same bound as well. And in fact, this is easier to implement because you can do this with kind of standard hash functions, whereas when you have without replacement, it gets a little more cumbersome. Okay. And just in matrix form, so this thing here really is what's your embedding matrix pi. For each column, you pick exactly s locations and put a random sign there. And here I've broken up the rows into s blocks, each of size m over s. Okay. So how do you analyze this kind of thing? I'm not going to go through the details of the analysis, but let me give you a little overview. So in both constructions, you can write the ijth entry of the matrix pi in the following way. Delta ij is a 0, 1 random variable telling you is the ijth entry of pi 0 or 1. Sigma is a random sign, and there's this normalization by root s. And in both constructions, you can write the difference between the projected vector's norm squared minus the original vector's norm squared, which is 1, as the following thing. And this is a quadratic form in sigma. You can write that as sigma transpose b sigma, where sigma is this m times n dimensional vector. And now, you want a tail bound. You want to say that the probability that this is big is small. Okay, and you can write out what this matrix is, B. So there's a closed form. Here I said u, here I said x, so x and u are the same thing. Sorry about that notational confusion. And the bottom line is the probability that this thing's bigger than epsilon is the same thing as saying the probability that this quadratic form deviates from its expectation. And you can use the moment method. And there is a moment bound that's known for quadratic forms. It depends on the Frobenius norm of this matrix B. And it also depends on the operator norm of this matrix B, the L2 to 2 operator norm. And once you bound those things, you plug it into the Hansen-Wright inequality, and you get exactly what I promised you. Okay? Okay. So I'm not going to go through that calculation, but that's how it goes. So next, what do I want to do? Okay. That's all I want to say about generic sparse JL. So let's move into something else. So I claim that there's a natural matrix extension of the sparse JL lemma. So what's the lemma I just claimed? If you pick an n-dimensional unit vector and pi is a sparse sign matrix, namely the matrices I showed you before, then with high probability you'll preserve the norm of u. As long as the number of rows is at least this and s is better by an epsilon factor, and you'll use the moment method with the log 1 over delta th moment. Or you can take the second moment with sparsity 1, and that's Thorpe-Zhang. Yeah. Okay. So let me be a little suggestive. And what's an n by 1 matrix of unit L2 norm? Sorry, what's a unit vector? What is a unit? I already said it, I guess. What's a unit vector? A unit vector is just an n by 1 matrix with orthonormal columns. Okay, ortho means nothing when you have one column, but it's true. And I'm trying to be suggestive here. Okay, so the thing I wrote on the last slide is exactly the same as this, where 1 is just the 1 by 1 identity matrix. Okay, so this is the same exact thing as the last slide. Okay, so conjecture, you should be able to have not one column, but d columns. Okay? And that should hold as long as m is the following thing and s is the following thing, based on the log d over delta th moment method. So I'm going to get back to, right. So using this moment, or you should be able to use the second moment and get that. Okay. Okay, so we don't know how to prove this conjecture right now, but we can prove something. And this is joint work with Hui, which is you can get worse by polylog factors in m and s. Or you can set m to be slightly superlinear, d to the say 1.01, and s doesn't depend on d at all. Or you can do the second moment method and get this bound. Yes? Yes, the spectral norm. Yes, L2 to 2 operator norm. And just a couple of remarks. So when m is d squared pi log d over epsilon s equals 1, Clarkson and Woodruff showed this via other methods, not using the moment method on the last slide. And using the moment method, using the second moment, Mahoney and Meng independently were able to get this bound as well, d squared over epsilon squared with s being 1. You can also get that bound using even another method. Basically, if you take Thorpe-Zhang and use some reduction, black box reduction in that work, you can also get this kind of bound.
Is that third thing that you mentioned?
Yeah. Okay. Another thing just about the moment method. How do you actually perform the moment method with matrices? Well, there's a classical way of doing it that people have been doing in random matrix theory since at least the 50s, which is, so what's the probability that this operator norm is bigger than epsilon? You do the moment method. This is basically Markov's inequality after raising both sides to the nth power. And then you use the fact that, well, if L is an even integer, okay, so what is this thing here? It's the largest eigenvalue raised to the L. Meanwhile, what is this thing? Well, this inner matrix raised to the L, its eigenvalues are the old eigenvalues raised to the L, and the trace is the sum. And since L is an even integer, everything here is non-negative. So the sum definitely dominates the max. Okay? So this is what I mean by the moment method when you're dealing with matrices. And okay, so why do we care about this matrix extension? The reason we care is the following. To say that the operator norm of this matrix is less than epsilon is equivalent to saying that pi preserves the norm of every vector in the subspace spanned by the columns of U. And there were some previous talks in this workshop about subspace embeddings. Okay? And the reason we care about subspace embeddings is you can use them to speed up algorithms for many numerical linear algebra problems on big matrices. Okay? And if pi is sparse, that means you can multiply pi times a. So if you have some big matrix A you're working with, you can multiply pi times a in time, which is s times the number of non-zero entries in A. So the sparser it is, the closer you get to this bound here. Okay, so let me just run through a little bit of numerical linear algebra. What time did I start, by the way? 9:30 or something? Okay. So let's say we have a big matrix. N is much bigger than D. So there are a few problems here. I'm not going to spend time on all of them, but let me just say a couple. So say least squares regression. You collected n data points. Each one is an RD. And you're trying to fit the best line to your data that you can. By best, I mean you minimize the sum of square distances to the line. Okay? So that's least squares regression. Low rank approximation is basically at the heart of, say, principal component analysis. And all these things get used in various contexts. Okay. So there are solid problems here. And for all these problems, you can use the SVD to get efficient solutions. So theorem, every matrix A has what's called an SVD, which is writing it as the product of three matrices in this way. The middle matrix is diagonal with strictly positive entries on the diagonal, and U and V have orthonormal columns. And once you have the SVD, which you can compute in this kind of time, there's some up to some precision, and there's some logarithmic dependence on precision. Okay, I'm not going to talk about precision issues in this talk. I claim that once you have the SVD, you can solve a lot of problems. Why? Well, let's look at least squares regression, for example. You're trying to minimize the L2 norm of AX minus B. What's the best X to choose? Basically, part of B lies in the subspace spanned by the columns of A, and part of B is in the orthogonal complement. You can't kill the part in the orthogonal complement, right? So you want to kill everything that's in the subspace. So you want to project B down to the subspace, and that's the X, that's the best X. And you can just read that off from the SVD. Low rank approximation, there's a theorem called the Eckart-Young theorem, which says that if you just zero out all but the top k singular values of this matrix sigma, that will give you the best low rank approximation under, say, Frobenius norm or operator norm. Okay? Great. So conclusion, we can compute the SVD, and then we can solve all these problems. Can we do better than that? So this is where subspace embeddings are going to come into play. So I want to show you how can you use subspace embeddings, for example, for least squares regression. There are other reductions for least squares regression, but I feel this is the simplest to present. And I'm not going to go through all the reductions for other problems. So by the way, this is known from previous work on this problem. So instead of minimizing AX minus B for the original least squares problem, these are all L2 norms, we're going to do it for the new problem pi AX minus pi B. And I claim that doing that gives you almost as good a solution as solving the actual optimal solution for the original problem. And why is that? Well, definitely this is true. X tilde is the minimizer for the new regression problem. Right? So it's better than opt for the new regression problem than the optimal X star. And then you just write, what's this? It's pi times a certain vector. That's a vector which lives in the subspace spanned by the columns of A and B. So as long as pi is a subspace embedding for that D+1 dimensional subspace, it's preserved. And similarly on the right-hand side, and you move things around and you get that. So pi just needs to be a subspace embedding for some D+1 dimensional subspace. And the bottom line is now you only need to compute the SVD of pi a, which is a lot faster, because you have a much smaller dimension. Okay? Okay. So now that I've shown you at least one way of using subspace embeddings, let's get back to how do you show this matrix extension of Sparse JL? So remember, we want to show, we have this kind of inequality. The probability this operator norm is bigger than epsilon is at most this bound here. And now, basically, we just need to bound this expected trace to some power. So how about the case where L is 2? I claim that if you take the trace to the second power, you can get a bound with sparsity 1 and m being d squared over epsilon squared. And taking L equals 2 is equivalent to what was in the work by Mahoney and May. Okay, so let's just introduce a little bit of notation. Let the columns of this matrix U be U1 up to UD. Those are the D vectors in our orthonormal basis for our subspace. And recall that pi ij can be written in this way. Delta tells you whether that entry is non-zero, sigma is a random sign. Some computations, which I'm not going to do here, yield the following. Basically, the point is you can write down a closed form formula for what the entries of this matrix are. Okay. And now, the trace of a square matrix squared, I mean, whenever a symmetric matrix, a symmetric square matrix, right, and you square it and take the trace, that's always equal to taking the Frobenius norm squared. So that now is just a computation, right? You know what the entries of the matrix are. You square them and you add them up, and you compute the expectation, and you get a bound. You get that it's at most that. You plug that into the Markov kind of inequality I showed you, and you set M. M should be d squared over epsilon squared to get this kind of thing. Okay. So that's how that goes. Okay. So now I want to move into how do you show the bound where M can be very close to D, right? Very close to D over epsilon squared with a little bit more sparsity. So that's going to be a larger moment. We're going to go to like the log dth moment. So I want to say a little bit about how that proof works. So first of all, whenever you have a square matrix and raise it to the nth power, what's its ijth entry? By induction, you can prove it's this. You sum over all paths going from I to j of some product of entries of the matrix. And the trace is the case where you're going from I to I. So it's the sum over all cycles, where the last thing is equal to the first. So what's our matrix B? It's S minus I. So you just write it down. Okay, it's a big thing, but the point is you can write it down explicitly. Okay. And how do we deal with this big thing? We use a strategy that random matrix folks have been using for a long time, which is you associate, so here you have a sum over lots of monomials. We're going to associate each monomial in this sum with a graph. Okay? It's not going to be a bijection. Many different monomials can be mapped to the same graph. Group monomials that have the same graph structure. And then what I want to say is the contribution of a monomial to this sum depends only on the graph structure, like the number of connected components or the number of vertices or the number of edges, et cetera. Okay. And then I'm going to get that bound and then do some combinatorics to count how many graphs there are. Okay? And this is kind of one of the bread and butter strategies of random matrix theory. But of course, we have to tailor it to the matrix at hand, which is this pi u transpose pi u minus identity. Okay. So I want to explain a little bit about how this monomial to graph correspondence works. Okay, because what I'm going to say in the remaining 20 minutes or so is not going to make sense unless I talk about this correspondence. Okay. So, for example, let's look at us taking the fourth moment. Okay. We're going to have a graph here that is going to end up having 4 L edges, so 16 edges. And how does this graph work? So there are 3 layers in this graph. Every monomial is a 3-layered graph. The rightmost layer corresponds to the R's here. The R's are between 1 and M. Those are like rows of pi. The middle layer, those are the I's and J's here. Those are like rows of U. Okay? Those are from 1 to N. And the K's are these K's here. Those are the columns of U. So that's from 1 to D. And basically what the graph is trying to capture is which R's are equal to each other and which I's and J's are equal to each other. Because it can happen that, say, I1 is equal to J3. And the graph will remember that because it'll use the same vertex for both of them. Similarly, if R1 is equal to R2, the graph will use the same vertex for both of them. Okay? There's going to be a little bit of asymmetry, which is that the graph is not going to remember which K's are equal to each other. That's K1 right here, that's K2 right here, that's K3, that's K4, and K5 is equal to K1. So there's always going to be exactly L left vertices. So now let me just run through how this looks. So we start at K1. This is how we draw the graph, going from 1 to 4, 1 to L. We start at K1, we go to I1, we go to R1, we go to J1, and then we go to K2. Now we move on to the next case, where T is 2. We start at K2. We go to I2, R2, J2, K3. And then we just keep doing that. And then we finally go back to K1. And then that's the whole graph. That's how you get a graph out of a monomial. Okay? And the edges are labeled in the order that we take them. So this is a cycle of the graph that starts at K1 and ends back at K1. So I want to make a few observations about what this graph structure is useful for. Like, why am I saying that you can bound the contribution of a monomial in terms of graph structure? So there are a couple things to note here. Every edge from the middle to the right is a sigma and a delta, right? Sigma Ri and delta Ri. So this is a sigma Ri right here and a delta Ri also. Okay? So look at the edge here from A to E. So that's like delta Re, that's like sigma Re Ia. It appears twice, that edge appears twice. What does that mean? It means that that particular sigma random variable got squared. Basically, the multiplicity of an edge is the power to which you're taking a sigma. Okay? And you have a product of sigmas which you're taking the expectation of. If any sigma is raised to an odd power, the expectation is 0. Right? These are random signs here. So in order for a monomial to contribute, every sigma has to appear an even number of times, even powers. Okay? So the only graphs that matter for us are graphs where all these edges from the middle to the right have even multiplicity. Similarly, how many distinct edges are between the middle and the right? Here there are 4. Every distinct edge is a distinct delta term over here. So what's the expectation of a delta term? A delta is like, is this entry of my matrix of pi 0 or 1? Its expectation is S over M. The probability that an entry is 1, the probability that an entry is non-zero is S over M, because there are S non-zeros per column. Right? So in this graph, the expectation of the product of the deltas is at most S over M to the 4th power. Right? So this graph is encoding a lot of information about the expectations. So let me move to the next slide. Basically, the thing you can show is that the expected trace of a large power is you sum up over all graphs that matter, meaning all these edges should have even multiplicity, of S over M to the number of distinct edges, B is the number of distinct edges between the middle and the right layer, M to the Z is the number of vertices on the right layer, that's 2 here, okay? Because you can choose basically who those R's are. And a sum over all assignments to the middle of dot products of rows of the matrix U. Where does that come from? If you look here, notice every vertex on the left has degree exactly 2. It connects 2 middle people. And when you sum up over the left, what you end up getting, you can show, is that this product, when you sum up over the left layer here, becomes dot products of rows of U. The dot product of A with B, the dot product of B with C, the dot product of C with D, and the dot product of D with A. In this particular graph, it's a 4-cycle. And I'm going to call this G hat the dot product graph that G is encoding. Okay. So highest level, where are we right now? What was the overall strategy? The overall strategy was we have a huge sum of monomials. Every monomial was a graph. I want to bound a monomial's contribution purely in combinatorial terms in terms of graph structure. So this is great. Number of distinct edges, number of vertices on the right, that's all combinatorial properties. Okay? And then I want to do combinatorics and say how many graphs are there that have all these parameters and bound that. But right here we have something that is not really fully a combinatorial property. Right? It's a sum of dot products of rows of a matrix that has orthonormal columns. So I want to bound this also in terms of graph structure, so that I can finally end up with something that's combinatorics. So how do I do that? I claim, I'm not going to justify this in this talk, that the right bound to get for the contribution of the dot product graph is d, the dimension of your subspace, raised to a power which is the number of connected components of the dot product graph. The dot product graph does not need to be connected. It doesn't even need to have all even edge multiplicities, as you saw in the last slide, right? This does not have all even edge multiplicities. But it still contributes to the final sum. And I also claim that if you're lucky and this graph has all even edge multiplicities, you can get this bound, which is d to the number of connected components. There is a proof of that. I'm not going to show it. Unfortunately, you're not always lucky. This does not have all even edge multiplicities. Right? So what do? So you remember that, you try to remember what this is encoding. This is encoding a product of things. This dot product times this dot product times that dot product times that dot product. So let's draw a little picture. This product of 4 things is the same as this product of 2 things times this product of 2 things. And let's draw an inequality of graphs, of pictures. By the AMGM inequality, arithmetic mean, geometric mean, this product is at most half of the average of the squares. That's the AMGM inequality. So I've reduced back to the case I can handle. I said that there is a proof, which I'm not going to show you, that handles the case when g hat has all even edge multiplicities. So I've reduced to that case. But there's a problem here. The problem is that I increased the number of connected components. Imagine that I have an L cycle and not a 4 cycle. I moved from one connected component, namely an L cycle, to having, no matter how you partition edges in an L cycle, if you do this AMGM trick, one of these things is going to have at least L over 2 connected components. And then you're just totally hosed. Okay? So how do we get around that? The way we get around that is the following, which I think really is kind of the contribution of what we do, because kind of the moment method itself is an old thing, right? So really the thing that required us to be a little creative was that we used the following theorem in a way that I'm going to show you very soon. There's this thing called the Tutt-Nash-Williams theorem, which says that if you have a graph with edge connectivity at least 2k, it has k edge disjoint spanning trees. Meaning, what is edge connectivity 2k? Every cut in the graph has at least 2k edges crossing it. Okay. I claim that if every connected component of the dot product graph has 2 edge disjoint spanning trees, we're done. Why are we done? Because over here, I could have partitioned this graph in any way I wanted. I could have partitioned the 2 edges any way I wanted. If it has 2 edge disjoint spanning trees, I'm going to place one spanning tree on one side, one spanning tree on the other side. I haven't destroyed the connectivity at all, AMGM, and now this trick actually worked without changing the connectivity at all. Unfortunately, the 4 cycle doesn't have 2 edge disjoint spanning trees. And unfortunately, many dot product graphs that you get don't have 2 edge disjoint spanning trees. So what do? Well, if some connected component is not 4-edge connected, if it doesn't have 2 edge disjoint spanning trees, then by the Tutt-Nash-Williams theorem, that connected component could not have been 4-edge connected. That's what the theorem says. What does that mean? It means that there's a cut with less than 4 edges crossing it. Well, you can prove that every connected component is Eulerian, meaning the number of edges crossing a cut is even. And we're focusing on a connected component here, so it's connected. So the number of edges crossing a cut is not 0. It's not 0 and it's less than 4, so it has to be 2. Right? And I can use that fact to make progress in the following way. So here's a connected component which is messing us up. It doesn't have 2 edge disjoint spanning trees. So by the Tutt-Nash-Williams theorem, it has a cut of size 2. Let's write down what that means in terms of this sum of products of dot products of rows of the matrix U. We have all the dot products specified by edges on the T side of the cut. Those are these dot products. We also have the edges on the T bar side of the cut. Those are these dot products. And then we have 2 edges crossing the cut. That's the dot product between the C'th row and the Ath row, and the Bth row and the Dth row. And I've suggestively underbraced something on the slide, namely all of this stuff, which is the stuff on the t-bar side of the cut. And what is the type of what I've underbraced? It's a matrix. So really, this dot product graph encodes the same exact information as this one, where you eliminate the t-bar side of the cut and replace it with a matrix. So here's the strategy. Repeatedly eliminate size 2 cuts until every connected component has 2 edge disjoint spanning trees. You're going to accumulate matrices on edges along the way. You prove a lemma that shows that all of these matrices you accumulate have bounded operator norm. And then you show that you can still handle even edge multiplicities even when you have these m's that have bounded operator norm. So you can apply the AMGM trick on the final thing after all these iterations and get the bound. And then now everything is in terms of combinatorial quantities, number of connected components, number of vertices, number of distinct edges. Then you do combinatorics. Okay? Okay. So conclusion, I think I have what? How much time? 5 minutes? Okay. So some other recent progress. One thing we can show is that whenever you have a subspace embedding that doesn't even need to look at the subspace, but randomly works with good probability, we can show that you need d over epsilon squared rows. Okay? Every subspace has a subspace embedding with d rows, with exactly d rows. But if you have to be oblivious to the input, you can show that you need d over epsilon squared rows. Another thing is we can show some trade-off, which is not optimal, I'll get to that on the next slide, between the sparsity and the number of rows you need in such an oblivious subspace embedding. Okay, the last thing I'm going to put on the slide. So let's be slightly more. Oh yeah, it's coming on the next when I click. Sorry, yeah. Okay. So I want to be a little more meta. So the JL lemma, as it's stated, says you have this set of vectors and you want to preserve it. And what we showed is what the sparsity needs to be and what the dimension needs to be. Then there's subspace embeddings. It's really the same problem, except the set of vectors I want to preserve is not an arbitrary set of vectors. It's a d-dimensional subspace. Then compressed sensing people care about RIP. What's that? It's the same kind of thing, except the set of vectors you want to preserve is, again, it's not arbitrary. It's the set of all k-sparse vectors in Rn. So then you could be a little more meta and say, let me prove a master theorem such that if someone gives me a set of vectors t and says, what's the number of rows I need to preserve t and what's the sparsity I need to preserve t, I can just give them an answer in terms of the geometry of t. So that's something that we were interested in, and we are able to provide bounds on the number of rows and the sparsity to preserve an arbitrary bounded set in terms of the geometry. So k-sparse vectors is one example, subspace is another example, arbitrary set is another example. And you can come up with lots of examples that you would care about. And if you don't care about sparsity at all, there's been a bit of work on that to show what m needs to be. But then S would equal m. Those are dense random matrices. And what we're able to show in this work is basically the sparse analog. If you care about sparse random matrices, what do the number of rows need to be and what does the sparsity need to be in terms of some geometric quantities that depend on the geometry of t, right? So if you give me a t, I can tell you what you need. And that's the star. Sorry about that. Yeah. I need to get better at Beamer so that that shows when it needs to show. Okay, good. So other open problems. I'll list them here, and I guess. Sorry? Oh yeah, I don't know how to. I don't know any. But the second, I don't know. So the third one, though, the third one really bothers me because we're losing these log factors in the moment method. But let's say you don't care about sparsity at all. You just want to show that d over epsilon squared rows works to get a subspace embedding. There's a net argument that will do it for you, not the moment method that I showed you before. And the net argument gives you the right answer. It gives you d over epsilon squared. But prove to me that same exact bound not using a net argument. Prove it using the moment method. I don't know how to do that, even with a dense random matrix. Then that really bothers me. If you take a dense sign matrix, I mean. If you take a dense Gaussian matrix, you can exploit some Gaussian properties. But basically, we're still losing log factors that we really don't need to lose in the moment method, and that bothers me. Also, the trade-off that I showed with Hui, m was d to the 1 plus gamma, and s had to be at least this. But we didn't have this epsilon squared here in our trade-off, and that's something that is wrong in the trade-off we prove. And there's also this last problem. So in the last, I guess, minute or two or whatever's left, just questions. Thank you.
So questions for Jelani? I have a quick question. So
Yeah.
in the work with Vaughan, like
Yeah.
you're saying kind of geometric properties of your set T, what
Yeah.
sort of geometric properties can jump up?
Sure. So it's probably easiest to explain, say, the previous works when you didn't care about sparsity at all. So what was the thing that came up there? So there's this thing called the Gaussian mean width of a set of vectors. So first of all, take T so it's normalized. So all the vectors in T have unit Euclidean norm. And the Gaussian mean width is you take a random Gaussian vector with, say, identity covariance matrix, and you look at the sup over all x and t of g dot x. That's the Gaussian mean width. And it turns out that the number of rows you need is the square of that. The Gaussian mean width for a set of n vectors is never more than root log n. So it recovers the JL lemma, for example. But if your vectors are well clustered, so kind of this Gaussian mean width captures the clusterability of your vectors in some very precise way. And if they're well clustered, you can get away with fewer dimensions. So, yeah. Yeah. Yeah, so except what we get right now is kind of rough, and there are lots of log factors that we need to shave, but yeah, we can get something also for a sparse, basically a sparse analog when pi is sparse.